Today is September 24th, 2020, and we are about to begin session 224 of the Zero Build Forum 20. The session is titled Zero Energy Buildings in Hot Climates, and we have three distinguished speakers today. We have Dr. James Mathias from Southern Illinois University, Carbondale. We have Dr. Ulrike Passe from Iowa State University. And we have Dr. Saleh Al-Saadi from Sultan Qaboos University in Oman. So first of all, I would like to welcome all of our distinguished speakers. It's good to see everyone in good shape. And I'm going to be introducing our first speaker, Dr. Mathias, first of all. Dr. James Mathias is an associate professor at Southern Illinois University, Carbondale. His research interests include better utilization of energy, particularly by using low-grade energy and renewable energy to a greater extent. He has been involved in the residential building sector. James earned mechanical engineering degrees from Brigham Young University and Ohio State University, and is a licensed professional engineer in Illinois. His presentation is titled Energy Efficient and Cost-Effective Solar House. With that, Dr. Mathias, I'd like to leave the floor to you.
Thank you, Dr. Çelik, for the introduction. Let's see if I can, oh boy. Okay. Let me share my screen. Does that look correct?
Yes.
Yeah. Okay, great. I can't see it because I can only see the presentation. All right. So, as Dr. Çelik said, the title is Energy Efficient, Cost-Effective Solar House. I'll give a little overview and then go through the design, construction, energy efficient equipment, results, and then propose solar panels, photovoltaic solar panels, to see if it would approach a net zero house, and then conclusions. So the objective was to construct an energy efficient house using commonly available products, and then analyze this house to see if solar collectors were added with the energy use approached zero. The house was designed using a heliodon, which is a device that shows how the sun shines on the house any time of the year, any day of the year, but particularly used to look at the winter and summer solstice. It had proper orientation with a lot of windows facing south and proper overhangs to allow the sun to shine in the winter, but not the summer. And it was faced actually a little bit east of south to allow the sun in more. The garage was on the northwest corner. Here's a picture on the heliodon. That's the picture on the top. And during the summer solstice, June 21st at noon, and then you see the actual house on the summer solstice, and it looks like a very good comparison. A large tree actually shaded the house. I don't know if you can see the cursor or the mouse, but you can see here there's where about the sun shines on the actual house, and this is where the heliodon predicted the sun would shine. And you can see in the summertime, the overhang shades the house. In the wintertime, the sun is lower in the sky, the tree has lost its leaves, and the overhang is predicted to about provide shade right there, and the actual house is shown right here with a large amount of the sun coming in the windows in the south side. Here's a picture of the inside of the house in the winter solstice at noon. Here's a floor plan of the house. Again, the larger rooms and the larger windows face south. The smaller rooms, such as bedrooms, had a typical size window, and those faced either north or the master bedroom faced east. It was made by commonly available wood in the US, which is a 2x6. We looked into thicker wood, but there's no windows or doors made to work with that thickness. And so we stuck with the thickness of 2x6, which is typical for windows and doors. Fiberglass insulation was used and every cavity was caulked. And this combination of caulking and fiberglass provided good, cost-effective, and good insulation. Airtight electrical boxes were used. Then a good typical double pane argon-filled window was used. Here's a cut view or cross-sectional view of the basement wall on your left-hand side, showing the insulation and the window and how the sun would shine in the winter and the summer. And then on the right-hand side shows the same thing for the upstairs of the house. A ground source heat pump was used to provide heating, cooling, and some hot water. A small unit was chosen because this good passive solar design reduced the amount of heating and cooling needed. A front-loading clothes washer conserved hot water and also reduced drying time with a fast spin cycle. Compact fluorescent lights were used when the house was built, but now LED lights are being used in it. Data was collected in 2007, measuring the heating, the cooling, the electric resistance heat, the hot water. There's a separate meter on each of those. And then the remaining electricity was measured by the outside meter on the house by subtracting the other meters. Also, the amount of heat gained from the solar sun shining in the winter was obtained using the electricity used by the heat pump, the outdoor air temperature, and solar radiation, which were measured from a weather station about 8 kilometers away. The correlation predicted 88% of electricity used. So it was a good predictor of electricity used, and it predicted that 23% of the heat came from the solar characteristics of the house. Here's a graph showing the white bars are the heat provided with solar energy. The black bars was the heat provided by the heat pump. Also, commercial software was used to simulate the actual energy use of the house. And that was calibrated using changing the schedules of lighting, appliances, bathing, washing. Once that was done, the schedules of those stayed the same, and the weather data stayed the same, but the house was changed to represent just a house built to code, which would be 2x4 walls, and all windows were assumed to be equally facing, same amount of window area, but equally facing all directions. And this showed then that the house built was used 50% less energy than the house built just to code. And some of that was, again, using back then incandescent lights. Here's a table showing the significant changes that were made: thicker walls, better windows, better insulation, and the amount of energy it saved or electricity it saved, depending on if it was electricity or heat transferred. And then the amount of energy the amount of cost that was increased price of the house due to that change. As you can see, the ground source heat pump had the largest price of the house increase, but also had the largest savings of electricity. If we assume that the additional heating and cooling provided by an air source heat pump with electric backup was about 10 cents a kilowatt hour, which is typical for this region, it shows annual savings from better windows during cooling of about $43, annual savings and wall of better windows and wall in the wintertime of about $124, and more efficient heat pump $464, for a total of about $632. If you look at a simple payback period of about 12 years then it was estimated to see if photovoltaic panels on the garage would provide a net zero house. The garage was chosen because the house has a large tree that shades most of the house. A 4.35 kilowatt DC system would fit on the garage, and in the Southern Illinois climate, this would produce in the first year 6,685 kilowatts of electricity. And then I looked at the house has now used more electricity. There was more occupants in the house, older occupants, and the house uses now, the last 12 months, 11,000 kilowatts. Here's an artist's interpretation, I guess, or the salesman's interpretation of what the solar panels would look like on the garage. And it wouldn't quite provide to make it a net zero house. I mentioned that if the tree were replaced or transplanted to maybe the front of the garage. And then another one of those systems would put on the main body of the house, which is the same orientation and the same roof angle. The power produced would be about the same, which would make it a net zero house then. The system that was estimated was a $13,000 US. The state of Illinois offers a credit of $6,600, and the US government currently offers an energy tax credit of off your taxes. If all incentives could be obtained, the system would then cost $3,000. In conclusion, the ground source heat pump with the water desuperheater compared to the air source heat pump provided the greatest energy savings. It worked well to obtain hot water in the summertime if we had two tanks. First tank was preheating the water, and the second tank was a normal water heater. Compact fluorescent lights and now LED lights had the shortest time to recover the cost compared to incandescent lights, which is very common. Also, some things that were learned was the house was very tight. A heat recovery ventilation system was installed to reduce moisture. A lot of moisture was obtained on the windows in the wintertime, and a dehumidifier is also used in the summertime. Currently, the photovoltaic solar panels were not installed. The homeowner doesn't claim a full credit of the federal tax incentive. That's more of the political side of things, but that was where it currently stands. That concludes my presentation. Thank you.
Thank you, Dr. Mathias. This was an interesting case study, and I know this was conducted in your own residential unit. Thanks again for your presentation. Now, we will be receiving the questions at the very end from the audience. So with that, I would like to announce our second speaker today, and then we'll leave the floor to her. Dr. Ulrike Passe is an associate professor of architecture at Iowa State University. She holds a professional architecture degree from the Technical University in Berlin and was already a licensed architect in Germany for 15 years before starting her academic career at ISU. She's the main author of Designing Spaces for Natural Ventilation, co-authored with Dr. Francine Battaglia in 2015. Dr. Passe founded a research group for sustainable cities decision-making in 2015, which recently received a $2.5 million NSF grant to research the interaction of urban food, energy, and water systems. She has published internationally in respected journals, and her Architecture 601 students have placed in the ACSA AIA Top 10 community in the environment in 4 out of 6 years since 2014, which I believe is a great success. I know how difficult and challenging it would be in such organizations getting those ranks. So with that, I'll leave the floor to Dr. Passe.
Well, thank you so much for the kind introduction, Serdar. I hope I can start my screen now. Give me a second here.
Sure.
No. Entire screen. Allow. Can you see this now?
Perfect. Yes.
Okay, great. So thank you so much. The title of my presentation is Long-Time Net Zero Home Research for a Warm and Humid Climate, or for warm and humid climates. And Iowa is obviously in the United States of America. And the acknowledgements here, the project was funded for many years also by the National Science Foundation, the Department of Natural Resources, and my own Iowa State Center for Building Energy Research consultancy, and credits to everybody involved. This is a large team project. So, of course, I'm an architect and I'm not a doctor. I was a practicing architect for many years. So the integration of sustainable design strategies into the built environment is critical for the survival of our planet. And in 2009, we built a house with students to fulfill net zero energy balance on the National Mall in Washington, D.C., our capital, for a U.S. Department of Energy competition. And just for those international colleagues who don't know where Iowa is, here we are, halfway between the Hudson Bay, cold Arctic climate, and the Gulf of Mexico, warm, humid, tropical climate. And that determines our own situation. So here are just a few data points. That's where it was on the mall in Washington. That's where it is now. It is re-established as a research center and an office for a state resort here in Iowa. The main building components are a very tight envelope, a traditional transformed porch, which can be a sun space in winter and open up for natural ventilation in summer, clear story windows for daylighting and shading elements on the south and the east facade, no windows on the west facade. Solar, thermal, and photovoltaics are providing the energy. The building is grid tied. There is no additional fossil fuel energy apart from the balance of electricity in case of need. So it feeds back and forth to the grid. We've done a lot of monitoring of the building. Lots of sensors were installed. As you can see, many students involved. The building has been monitored completely annually for the last 10 years. And so research objectives obviously is to investigate how the building works in its own climate, challenging climate, -6 Fahrenheit, -20 Celsius in winter, clear skies, snow, summers, 38 degrees Celsius, very humid, pretty much like Florida. And so we wanted to study the building, we wanted to validate computational fluid dynamics, and I wanted to prove that natural ventilation is possible in the Midwest, at least in the shoulder season. So here you see the sensor points and the layout of the building's floor plan. The porch can be opened up and closed. There are movable walls depending on the season. So it does need interaction of the occupants. Bathroom in the northwest corner, mechanical room in the northeast. Here are some pictures of the interior and the various strategies for passive design and the changeability of the building based on the season. A couple of pictures here, the sun space with thermal mass, shading necessary, high efficient envelope. You've heard this before. That's essential for our cold climate. Vacuum insulated doors, small windows on the north side. Monitoring through infrared cameras, finding all the points. Lower door test was conducted. High efficient triple pane glass here. Double layer walls. We also worked with existing structural strategies in the Midwest, 2x6, but in addition, furring with additional layers of insulation, leading to an R30 in the walls and R45 in the roofs. Electrical and thermal system here, hot water floor, solar hot water tank, and an energy recovery ventilator. So those strategies needed to be validated for the climate from the design through prediction into monitoring. Daylight was one of the major strategies to reduce electrical consumption through the northern windows, which can provide daylight even if the southern windows are shaded to reduce solar radiation. So we calibrated a transient fluid dynamics model. And for those who don't know what that is literally taking a gridded computational investigation tool into the air and model flow and temperature difference based on that flow. And so those models are very challenging to calibrate for natural ventilation. For low velocity flow, it's easy for a turbine. So we used the building to do just that. And here are here's the winter configuration with the sun space closed and the simulations in comparison here. And this is the outcome with the airflow through the warm air from the sun space flowing into the interior of the building. Open floor plan is essential for passive solar from sun spaces. And the summer configuration, you open the doors, you reduce the footprint, and one can here see that the window acts also as a ventilation inlet for the natural flow. And here you see the overview. We used vertical sensors 1 foot apart to validate those models, as you can see here with the students, and the various grid points or grid coarsities were studied. Here you see one experiment over a fine grid. Of course, that is more computational time, so there was more study necessary. Here just a picture to see the openable windows. And then, you know, we improved the model, and you can see that here now with the medium grid, you meet the data points for the experiment, which is literally incongruent with the simulation. And this is the height of the space. And so in order to validate further, we then said, you know, my major strategical hypothesis is that it's not just the stack ventilation which creates the comfortable environment, it's also the connectedness of spaces for multiple configurations. And so we said, you know, we tested once with the connected spaces and when we just take the model apart. And so you can see in the next, the connectedness of the spaces, the air takes its most possible path in the building. And if you take it apart, the building, which is only one bay, you know, up and down, the stack ventilation, the building air warms up to a higher temperature. And that's just the flow path. So the next study we did is to test the interrelationship of multiple comfort parameters in a passive solar daylit house. And that means another study was conducted using daylight sensors. And my telephone is going in the back. I'm sorry, I didn't turn that off. I didn't anticipate that coming. So daylight and natural ventilation is one, the windows on the top there. And we studied the relationship of thermal comfort and daylight comfort. So when the front windows are closed to reduce solar radiation, was there still sufficient visual illuminance without turning on the lights? And that we call that dynamic daylight understanding. And here you see, I mean, our designers probably know on the audience that there are certain set parameters for electrical illumination, 300 lux for offices, 250 for residences. But in daylight environments, those numbers sort of fluctuate significantly across the day. And so we wanted to find out when is actually the threshold when people turn on electrical light. And it's literally around or below 250 lux, as you can see here. And of course, one important parameter is the optimization of occupants control. And you see we're in Iowa, somebody is mowing the lawn in the background. Optimization of occupant control is important. So we installed a significant monitoring system with the data. Set points for heating and cooling was installed so that the occupants could actually set those goals themselves. And I have to close those. Give me a second. Yeah. I'm practicing what I preach, so I use natural ventilation all the time. So here you can see also the monitoring of the electrical consumption. You see small and large inverter. We have 2 inverters for the PV array on the roof. And you see here green means into the grid and over the year, sometimes the grid feeds back into the building. That is, of course, when it's cloudy or very cold. But passive solar and active solar are very good strategies in a sunny, cold climate, because PVs are actually more efficient when it's cold. And here inverter efficiency calculated, and the photovoltaics here, DC current, voltage, power, output. We monitor that over, we had 1 year where we really sort of monitored everything to the last digit, and also included occupants' behavior. And that, I think, is an important aspect for net zero design, is that the buildings and the occupants have to be working well together. And so we did a couple of controlled occupancy experiments. The occupants were informed about the weather, about the forecast of the weather. We have here a weather station on the roof, and you see here just an printout of the interface. The occupants could see and make informed decisions about the future of the operations. You know that when you have thermal mass in a building, you need to cool it down or warm it up depending on the next couple of days. So we informed the occupants of in various potential operation strategies: opening windows, closing windows, opening this window, opening that windows, closing shades, not closing shades, depending on what the next day would look like, and gave them a graphically, hopefully understandable scale of the temperatures where they should start thinking about the various strategies. So passive ventilation when it's below 75, and then they could switch to active mechanical ventilation when it was also too humid, which is the case in July and August. And so here the measured data, the experiments, the occupants when noted in a sort of spreadsheet in a log when they opened which window, and we sort of studied how that overlapped with the measurements: 60 hours, nighttime cooling, latent heat removal, active system use, and so on. And we overlaid that with the so-called adaptive comfort model, which is, I think, now integrated in most international, in the ASHRAE, certainly in the US standard for thermal comfort, but probably also internationally. I know in the UK it's very common that occupants are considered to be more tolerant with warmer temperatures when the building is, first of all, under their own control and naturally ventilated, so that there's more breeze, more air movement. And so we overlaid the measurement points and the comfort of the various experiments with that chart, and you see that most of the data points of the experiments where the occupants were using natural ventilation were inside those comfort parameters also. So validating both ways, what we have as standards is also possible with the humidity in the Midwestern Iowa climate. And then we modeled with Energy Plus here, simulation tool, probably known to a lot of people, developed by the US Department of Energy, the savings. And that's important here, depending on how often natural ventilation was used, obviously up to 100% cooling savings can be achieved. And that's huge in a humid, warm climate when you don't need cooling, because the major energy load for cooling in the Midwestern climate is the removal of humidity. But of course, there are certain times when the active system has to be turned on. So we also looked over the whole year with the operating strategies and the mechanical system. Just for those who are interested, this is how it looks. It's basically 2 big water tanks, evacuated tubes, photovoltaics, air handler, energy recovery ventilator, and some electrical systems. And so looking at the whole year, our challenge in the Midwest is not the humid summers. It is the really cold winter nights when there is no sun. and the desire of occupants to achieve comfort early in the morning, when the sun is not yet hitting the southern facades and the south-facing roofs. Then the backup electrical system is used too often in order to heat the radiant water system. So we did nearly meet net zero, as you can see in the blue line, but not fully, which is a learning curve. And I think everybody who's trying to do net zero buildings, one has to understand it has a lot to do with how people interact with the building. It's not just, it is the design, it's the least important is the mechanical system. Sorry, engineers, it is the people occupying the buildings. So we develop more operation strategies here, you know, what to do when, and when it's raining, when it's sunny, when it's hot. And we hope that that will now be applied to the next monitoring cycle. And we hope that we'll sometimes get to the zero number over the year. We talked with the public, the visitors. The good news is that the building is publicly accessible, so we have lots of visitors and we can use the building for education and outreach. See, positive. After visiting, even more positive. And here's some comments. And this is the important part, you know, the building will look different. The cities we'll build will need to be different, and we have to take our communities with us if we want to get to net zero. So here are my strategies, takeaway points, careful simulation based on a variety of schedules, set points, operation scenarios to anticipate and discover potential challenges of the climate. And the next research, we are currently working on that. You heard I'm working on the sustainable cities team now. We have to work on the urban context in order to get to net zero for the buildings. Buildings cannot be looked at individually. They have to be looked at as a community integrated system. And so here are my lessons, my future work. Real-time data collection is essential. Improved energy models are in the works. And the control strategies in some cases have to be automated when occupants are, for example, not present or are not willing or interested to actually monitor all these systems themselves, so that the building keeps being comfortable but uses the optimum strategies for operation. And with that, I'll credit all my research collaborators here. Multiple faculty were involved, postgraduates, graduate students, and for the monitoring, a lot of undergraduates who wired and installed sensors. So I'm really grateful for the big team I was able to compile here. And we've also published a lot. There are book chapters and many papers. You see a few here, all with the students. So I'm also using the house as an educational tool for architecture and engineering students at Iowa State University, and I'm happy to take any questions. Here are my contact information. Thank you so much.
Hey, thank you, Ulrike. Another interesting presentation. I was happy to see a wide list of undergraduate students there. I'm a strong advocate for involving undergrads in research, and you have quite the list there. That's a great benefit to them as well. Okay, so now we are to continue with our third speaker, Dr. Saleh Al-Saadi. Dr. Saadi is an associate professor of building energy systems and the program coordinator of the architectural engineering program at Sultan Qaboos University, Oman. He holds a PhD in architectural engineering from the University of Colorado at Boulder, a master's degree in architectural engineering from King Fahd University of Petroleum and Minerals, and a Bachelor of Civil Engineering from Sultan Qaboos University. Dr. Saleh has a diversified work experience in industry and academia. His current research interests include modeling, design and analysis of building energy systems, energy conservation, energy auditing and retrofitting opportunities in existing buildings, renewable and sustainable energy applications for buildings. So it's always a great pleasure to listen to someone with both industrial and academic experience. With that, Dr. Al-Saadi, I will leave the stage to you.
Thank you very much. Do you hear me? My voice is clear?
Yes, yeah, we can hear you.
Okay, great. Can you see the presentation? Are you able to see the presentation now?
Not yet.
Not yet. What about now?
Yes, now we can see it. Thank you.
Okay. Okay, great. Thank you very much for introducing me. So the title of the presentation is going to be Zero Energy Building in Hot Climate of Oman. In fact, it's an extreme climate. I'm going to talk about the design of this house and the energy performance analysis. Where is Oman? Maybe perhaps many of you don't know where is Oman, so I want to put a highlight here. So Oman, the Tropic of Cancer passes through the capital city of Muscat, in Oman, the capital city of Oman, Muscat. Oman lies between 15 degree to 26 degree north of the equator. Muscat, the capital city, is here. So where you have the Tropic of Cancer that passes over it. Oman has diversified climates. It can be categorized according to this map here, where we have a coastal area, and it looks like something like this. And then we have the desert area. Not all of it is going to be like this, but most of the areas here is with sand dunes. And then we have the mountain area, Oasis as well. And then on the south of Oman, we have monsoon kind of effect. Energy status in Oman. Oman depends a lot on fossil fuels for producing electricity. The main source is natural gas in all the big cities. And we are using diesel in remote areas where electrical networks are not available. Perhaps 98% of our electricity is coming from natural gas. Looking into the electrical consumption of building sector in Oman, this is a recent statistic that is published by the Authority for Electricity Regulation, which now has been also changed in terms of the name. According to this statistic, residential buildings consume around 45% of electricity. Commercial buildings consume 24%, and governmental buildings consume 12%. In total, we can see that the building sector alone consumes 81% of electricity produced in Oman. So in 2012, the Research Council has come up with an idea of inviting all the academic institutes in Oman to go into a competition of designing and operating eco-friendly houses, and that is part of trying to solve the current energy crisis in Oman, where you can see that the residential buildings consumes around 45%. The peak electricity in Oman is also another major problem where the government is not able to or it's like a financial burden to the government to build new power stations just to meet the peak demand, which happens in 1 month of the year. So the Research Council of Oman, TRC, took that initiative and tried to spread the idea, have a net zero energy buildings prototypes. We call them sustainable buildings, in fact, because it considers many parts, many areas of sustainability rather than only the energy part. So during that time, in 2012, they have invited many institutes, more than 10, between 10 and 15 institutes, but eventually they selected only 5 because the budget was limited, and so also for other reasons as well in terms of design and so on. 3 of these houses were built in Muscat, the capital city of Oman, which is characterized to be a hot, humid climate because it is nearby the coast, the Gulf of Oman. 1 was built in Nizwa, which is in the desert area, or in Oasis area, which is a hot, dry climate. And another house was built on the south of Oman, which is warm, humid climate. Sorry for the mistake. So this one is a warm, humid climate where it is affected by the monsoon effect in summer. This is how the houses look like. The first one is the Higher College of Technology. Now they changed the name to the University of Technology and Applied Science. This is the house, this is the actual house, and this is the rendering of the house. The second house, this one is in Muscat, and the second one is also in Muscat, and it is designed and built inside the German University of Technology in Muscat. This is the actual picture of the house, and this is the rendering. And the third one is also in Muscat, and it is done by Sultan Qaboos University. This is the rendering, and this is the actual. This is in Nizwa University. This is the actual and rendering, and this is in Dhofar University. We are going to talk about the one in the middle. Other houses, we are not going to talk about them. Definitely, they have a lot of new things, and in fact, every house has a different system, whether it is in terms of the form or the design strategies, either passive strategies or active strategies or renewable energy. Our eco-house at Sultan Qaboos University, as I said, it was funded by the Research Council and partially also by our institute. The total cost the total fund we received from the TRC was around 120,000 Omani riyals, and we got additional 40,000 from our institute. For you to make a conversion, 1 Omani riyal is $2.6 or it is 19.46 Turkish lira. The built-up area is around 278 meters square. It was completed in 2014. This is the floor plan of the house. It is 2 floors. This is the ground floor. We have a majlis, which is a male guest room. In Oman, the female and male usually are segregated. So that's why this was designed in this way. We have family area here. We have kind of guest room here, dining and kitchen. The form is an interesting thing here. You can see that it is in H shape, where it captures the wind or the natural breeze from the sea, which normally comes from the northeast of Muscat. And then we have windows here. We have a fountain here. An interesting thing also, you can see an additional structure outside the building. This structure is to protect the house from the solar radiation. This is the first floor. We have a void, or there is an opening between the family room and top floor, a circulation area, and then we have master bedroom and living room, boys room, and girls room. During the design, they have the design team, of course, similar to other institutes, involves students, faculty members, and designers also from industry to oversee and get the permission to build the houses. There were considerations of the form, the geometry, natural ventilation, as well as in envelope design and shading systems, sustainable landscape and microclimate to also help to reduce the outside temperature, wastewater treatment and irrigation. Also, we have used some technologies to treat the black water. We use also renewable energy system. As I said, that the main objective of the project was not about net zero energy building. It was about developing a typology of eco-friendly houses that are sustainable and considers the resources in general, which is energy, materials, as well as the water. In terms of the envelope, you can see that we have used the thermal blocks or air-rated concrete blocks, the white blocks. At that time in 2012, when we started building the houses, these kind of blocks are not in the market. And that is one of the challenge for any sustainable buildings, because sustainability also considers the transportation cost and emissions as well. But unfortunately, at that time, it was not possible to have such kind of materials in-house. We can see that first of all, the wall is a cavity wall where you can see the outer leaf. It is a thermal block, and then we have a 5 centimeter of insulation, and then we have another leaf, interior leaf, that is also a thermal block. In terms of shading, this is the exterior shell that on the top floor we are covering it with canvas with different also colors. On the bottom floor, we are covering the double shell with the green wall, as you can see, the green wall. All these openings at the shell, the outer shell, are covered by date palm trees, which are abundant in Oman. So we have contacted local people to develop these date palm trees shading system and treat it, and then install it in the house to be like a sustainable materials for shading. This is the courtyard where we have a fountain. This is the fountain, and you can see the outer shell that shade the house from the sun. You can see the sun here. At later stage, we also installed a mist spray, and that is mainly to change the microclimate in the double shell area. In terms of glazing, we use double glazing, and we use the glazing also was clear glazing. We didn't use a tinted glazing because we have an outer shell that should block the direct sunlight, and then we have diffuse light inside that comes from the small gaps that you see on the roof where the daylight should go in. In terms of the material, the design of the frames, aluminum frames, you see that we have thermal breaks that should improve the thermal performance of glazing. On the roof side, we have used wood. As you can see, we have wood materials here, as well as PV panels that are tilted 23.5 due to south. 23.5 because Muscat is located at that latitude, and that is normally is considered an optimal tilt for PV panels. In terms of solar radiation, we have utilized 20 kilowatt of PV system on the roof. We also use the solar water heater to heat the water. Inside the house, there is a very I will not say complicated, but a decent system of data acquisition, where it measures the indoor thermal environment. In that case, you can see this is a globe. This device measures the globe temperature as well as the air temperature and the relative humidity. And we have 10 of this in 10 spaces. Each instrument that you see on this slide are connected to a central data logger, where it collects all the information from the indoor thermal or indoor environment sensors, as well as we have a weather station on the roof that measures different weather climate parameters. We have also sensors that measures the water and irrigation, and we have current transformers that measures the different electricity end users, like the air conditioning system, lighting system, and all other appliances. And in addition to that, we have a smart meter that measures the electricity in and out. And we, in 2014, we got a special permission to install this, because at that time, only 5 eco-houses had the opportunity to install this kind of meters, because they were not available in Oman. All this data goes into, as I said, into data logger, into a central data logger, where all the information goes into a website that was under the Research Council for the monitoring purpose for the competition. From 2014 up to 2017, we had, we received many people coming inside the house, looking into the systems, checking what are the innovative ideas, whether they are architectural or engineering systems, sustainable systems, and so on. And the question that we always get, whether the house is a zero energy, is it a real zero energy building or it's not? And we didn't have an opportunity to provide this or to answer this question, because we didn't test the house. So we decided in April 2017 to measure the electricity inside the house, and it was from April 2017 to April 2018. You see two graphs or two bars, two charts here. The first chart here, A is measuring the load in the house, and which is in red, and then you see the green bars here measures the generation from the PV system. This is the monthly over the monthly for the whole year. I would like also to say that during the monitoring, we did not operate the whole system. We were only operating the air conditioning system, because electricity in Oman is dominated by air conditioning system, because it's a cooling dominated climate. In addition, it was not easy to monitor lighting and other appliances, because you need to have people who are living inside, and as we know that definitely the occupants will have a major impact on the energy consumption of house. The second chart, which is on the B, it shows how much energy is exported and how much energy is imported. Of course, subtracting the energy that is being used by the house, because that is the first priority that comes from the PV here, and it is expected whether it is on this chart or in that chart, that the energy or the load will be higher in summer, and it will be lower in winter. And an interesting also thing to see that even in we can see that even in winter, although we don't have an air conditioning, a lot of or high load on air conditioning system, but we see that we are also imported energy because we didn't have battery in the house where it can store the energy. So therefore, we were exporting a lot, but during the night, we were also importing some of the electricity. Because of this monitoring campaign that we did, we were able to say that this house was in a deficit of 860 kilowatt hour to be close to a full net zero energy building. Keeping in mind that in this campaign, only air conditioning system was operating. In a real setup of evaluating whether this is a net zero energy building or not, you need to have occupants, and the occupants need to be guided, and they need to be informed of how to use the house. And most probably during the winter period, which is January, February, and March, and then November and December, most probably the AC will not be operated. And during April and October, maybe September, you might also use natural ventilation because outside temperature is not that hot. So I agree with my colleagues that the human behavior is one of the most important thing, and it is one of the driving potential of achieving a net zero energy building. You might have a net zero energy building, but if you don't have a proper and educated occupants on how to deal with it, they might not achieve the net zero energy. Another way of looking into the information that I have presented is to see how the whole thing, the energy, for example, the primary energy or the site energy, is drawn on a zero balance line. So this chart here shows the house load in terms of kilowatt hour per meter square. This is the primary energy that takes into consideration the electricity that is produced by the power station. And then the house load will move to this point here because of the self-consumption from the PV. And then this point here will go up to the line of zero balance line, and it will export the extra electricity that you have. If you are on this line, it means that the house is a net zero energy building. If it is slightly below this, then it is a nearly zero energy building. If it is above, then it's going to be a net positive energy building. Obviously, in our
Dr. Al-Saadi, 2 minutes if you would like to wrap up.
I'm almost there. So if you can see also that the point here is below the line, and so therefore the house can be categorized as a nearly zero energy building. The same situation for the site energy as well as CO2. But an interesting thing is here, because in Oman, they are using a different tariff for selling and buying. For selling, we have a feed-in tariff where the electricity price is higher than the block tariff. The block tariff is what we buy from the government, which is subsidized. So in this case, the house was going to this. The green point is becoming on the positive side of the line. If we had the block tariff, if we sell the price similar to the buying price, then still the point is going to be below. So I was planning to give a video about the Ecohouse, but since we don't have time, I will just give up on this point. And thank you very much.
Dr. Al-Saadi, if it's not a long one, why don't you share the video with us?
It's around 5 minutes.
Let us take a look at it before we get to the Q&A session. Thank you.
We live in a world full of life, full of color, full of beauty. The environment is that area in which we're born, live, and interact. Through years, humans learned how to take advantage of all resources of the environment to improve their way of living, and they succeeded. But unfortunately, things do not remain the same. These resources began to diminish, and environment starts being threatened. At SQU, we decided to face these challenges and the need to find other solutions.
SQU Ecohouse responded to Omani traditional dwelling by introducing a unique design innovation of combining the traditional courtyard with traditional air scope. It aims to reintroduce sustainable living patterns. The Ecohouse was oriented towards north and south direction and was given each form with north and south courtyards, which are in direct contact with the central family living room to enhance the interaction between indoor and outdoor environment. Double shell system was used in SQU Ecohouse. A secondary light shell is placed outside the main shell to intercept and dissipate most of the solar heat impact before it reaches the main shell of the building. The landscaping is designed in a way to enhance the thermal performance of the Ecohouse. The landscape is recycled black water to reduce the wasted water. The fixtures used for the Ecohouse bathrooms is the EPA WaterSense labeled fixtures. These fixtures use 20% less water than the standard fixtures. LED lights throughout the home uses 80% less energy than standard incandescent bulbs and lasts 35 to 50 times longer. Although they are more expensive than the incandescent bulbs, they will pay for themselves in less than 3 years. Thermal comfort can be achieved by natural ventilation alone for 4 months. Architecturally, this is achieved by locating inlet windows at low levels and outlet windows at higher level to expel hot air.
Solar energy is one from the most important resource for renewable energy in Oman. So we use the solar panel in the Ecohouse to produce 20 kilowatt to provide power for the house during the day. The system is divided for 4 arrays. Each arrays have 20 solar panels. The total panels in the roof is 18 panels. We can use the Ecohouse system as a standard to produce renewable energy for any houses in Oman that can use a solar cell system to provide power during the day, and also we can using the grid.
SQU Ecohouse is an attempt to promote sustainable residential development that suits Omani society within a national competition initiated by the Research Council. At SQU, we believe in preserving our environment, which is a wealth in our hands.
Thank you very much.
Perfect. Thank you for sharing the video, Dr. Al-Saadi. I would like to thank all 3 speakers. Now we are into our Q&A session, and I will go in the order that we have received the questions, and I also have some questions also to the speakers. In the meantime, if any of the speakers have any questions to each other, please feel free to bring those up as well. So the first question is for Ulrike Passe. How can we convince the municipalities for long-term district level interventions? It seems there is not much progress at the municipality level policies are changing each time the mayor changes, is the question and the statement. Ulrike.
Well, elect the right mayor, I would say. But
that's the visual,
yes, I mean, I can only talk for the US context. I know also some European context, but I think mayors and municipalities can be convinced just by pure numbers, and also by understanding who those strategies serve best, and that is often those who have the least. And so I think it's important to understand there is a big move in US municipalities towards sustainable urban development. Many municipalities have more restrictive guidance than is anticipated across or outside of the US. So I think just pure reason, that's what I would say. And, in the Midwest, we have a lot of progress in that regard. So it's hard to answer that question, definitely.
Yeah, I agree. I think not only...
It needs a lot of convincing and a lot of discussion. And I think it's just, trying again and again and again. Reason will prevail.
Yeah. I think not only within the US, but, in different parts of the world, again, the nations and the cities have different approaches. So I agree with you that convincing usually is the issue there. Thank you, Ulrike. So I received some questions for Dr. Al-Saadi, and I know some of these questions were partially answered after we received the questions, but I'll still go ahead and ask the questions, Dr. Al-Saadi. So, are there any incentives for zero energy buildings in Oman, and what steps are the state taking? Is one of the questions to you.
If we talk about installing a PV system on the top of the houses, there are incentives because you can buy the electricity at subsidized cost, but then you sell it at a real cost. That is one of the incentives, but that is not you cannot install a PV system on top of house and then you can say it is a net zero energy building, because you need to have a proper design. In terms of the design of architectural design and engineering design, unfortunately we don't even have a code. Those people who have designed the 5 eco-houses, they have used their own codes. So those from Germany, they use the German code. Those from, it depends on from where the architect, comes, and therefore they introduce their own code. So up to now, we don't have a code that considers the sustainable buildings or net zero energy buildings, except the structural code and architectural code. That's it.
Okay, thank you, Dr. Al-Saadi. Another question for you. One of the audience here is asking if you could elaborate more on the mist spray that you mentioned.
Yeah. So the mist spray are basically you have a high pressure pump, and of course that is connected to the water lines, and then from the high pressure pumps you have a small tiny pipes that goes around the building, because we have a double shell, and then from there you have sprays, you have nozzles into microns, and those nozzles push the water, and you will have like a very small drop of water that goes into the double shell, and therefore it should use the evaporation process to cool down the air which is in the double shell, which consequently reduces the air temperature and therefore the heat transfer across the building. Although we have a hot, humid climate in Muscat, but the SQU campus is located somehow near the mountain, with between the coast and between the desert area, where during the night the air changes its direction and the hot, dry air comes from the mountainside. So therefore, we found that it could work. Up to now, we didn't test the functionality of the mist spray, because it's not an easy thing really to test systems, but we are sure that it does have a good impact.
Okay. One more question to you, Dr. Al-Saadi. One other member in the audience has asked the reason for you preferring wood instead of white pebbles.
I'm not sure about the white pebbles, whether they are available in Oman or not, but those wood were locally available, and especially those which are used on the roof. They normally just throw them into the so it's like a waste. So we have used those to for shading. So I'm not sure about the white pebbles.
Yes, my guess was when I read the question whether they were some landscaping rocks, but yes, I think it was kind of vague there. Thank you. So Dr. Mathias, I have a question here for you from the audience. Why do we need passive solar houses for regions with hot climates? And what are the advantages and disadvantages of passive solar houses in hot climates?
Good question. I gave a similar presentation to international students. They many times ask faculty to speak. The students take a course to help acclimate them to English and things like this. And so I gave the presentation and I asked if any of their countries did something similar. And that one student from Saudi Arabia said, we always face our windows north. And he said, we don't want the sun to come in at all. And I started thinking, if you don't want heat, if you don't need heat at all, then I would agree. You could still do passive solar, but you would do it very differently in the sense of more windows would face north maybe, and it'd be more natural lighting, but not direct lighting that comes in. I don't think you'd want any windows to face west. That is the hottest sun, and always it always shines directly in when the sun is setting. So I guess I grew up in a colder climate than Iowa, even in Minnesota. And so we always have this heating in the winter and air conditioning in the summer. But yeah, if you don't want heat at all, then the same concepts can work, but obviously you face your windows opposite directions.
And then another question I had when I was watching your presentation is the ground source heat pump. So when it comes to any geothermal, or in fact, this might be a question extended to, Ulrike also, when there is the ground heating. When we bury the pipes underneath the soil or underneath the wooden floor, let this be a question actually to both of you, there is always that risk of the pipes leaking, which is a lot of cost actually to fix it. Have you experienced such a problem, or have you done any study on the cost of maintenance and fixing such a potential problem?
I'll start and then she can continue on. I think hers are more on the floor of the house, which shouldn't shift too much. Mine are outside the house, 50 feet deep and six tubes. And they used to do just copper pipes out there called direct exchange. It was actually the evaporator in the wintertime and the condenser in the summertime. But they found that as the soil shifted, the copper pipes broke. And like I said, the system was inoperable then. So mine are plastic pipes that have a little bit of flexibility to them built in. So as the ground shifts, I've had no problems at all. The grounds naturally shift as you obviously build the house and then backfill it in. So they purposely put a plastic flexible section on each pipe to allow it to move and not break. And I have water flowing through the pipes and it comes back to the heat pump. I just have air circulating through the house, not underground heat.
Are those just like shock absorbers in between the pipes?
Think of it as a flexible plastic. Not the solid PVC, except for the very bottom is a solid PVC welded on, but the other ones are flexible tubing.
Ulrike, would you like to elaborate more on it?
Yeah, I mean, a ground-coupled heat pump is something else than a radiant floor system. So, I mean, we didn't use any ground-coupled heat, although it's a very proven technology in the Midwest because our soil temperature is very good for, cooling in summer and heating in winter. But the radiant floor in our building has been there now for 10 years. It's also proven technology as PEX tubing. I mean, you should just not drill a hole through the floor, I guess, but who does that? So it's a continuous loop, and we have no problems. I mean, radiant floor systems are also very proven technologies. This one is based on a timber floor bed and aluminum. It's not embedded in concrete, so it's I mean, a lot of buildings are heated with hydronic systems.
I think the piping system just reduces the risk, but I remember back in the day that leakage was an issue, and you could figure out where water is by some detectors, but that even by itself is not helpful, because if it's ceramic tiling and where water accumulates might just be misleading, if there is any sort of a slope underneath the marble or the ceramic. So you could just be breaking the wrong part of, say, the living room or the kitchen.
Yeah, sure. I mean, every building needs maintenance and needs to be built well. So
true. Okay, well, these are the questions that I received from the audience, and I had myself to you. Are there any questions of the speakers to each other, or any comments? Well, if not, then
I have a question. I have always interested to install the tubes within the envelope, and then either use a ground source heat pump or use a evaporator kind of mechanical system outside. I'm not sure whether that will work in Oman or not, because we haven't measured the ground temperature. We don't have sensors, but I'm not sure. I'm not sure how that. Will it work or not work? So I would like to get the opinion of the professors with us about their experience, or any advice on this.
I mean, if I may say, I don't know the ground temperature in Oman, but I would assume it's above 75 degrees, right? So then you have 75 degrees is not really a temperature for cooling. In Iowa, it's 55. I would assume in Illinois, it's pretty similar ground temperature year round, which means that you have a delta T, which you can use to cool the building. So I think if the ground temperature is above comfort temperature, you would probably have a hard time using a heat pump. I mean, that's just my understanding of the system. So
my comment is, I've heard that if you need to air condition all year long, the ground will also, not only is it pretty warm to start with probably, but it will get warmer and warmer and warmer as you run the ground system. Mine, it gets warmer and warmer in the summertime as I put heat in, but then in the wintertime, I'm going to take heat out of it and bring it back to the initial temperature. I'm in Southern Illinois, so I'm about 60 Fahrenheit now, is maybe 15 or 18 Celsius. And so I think it's great to have it works well in climates that are hot and cold, because then you can bring it back to the initial condition. Whereas I heard if you're too hot, you don't ever take heat out of it. It gets warmer and warmer and it becomes ineffective. Same point, if you live in a really cold climate, you would take so much heat out of it, you would never warm it back up either.
Thank you. Any other questions? Any comments? Okay, well then I would like to thank again all speakers for the great presentations, and I hope to see you in future events somewhere else. You all take care and stay safe.
Yeah, thank you so much for moderating, Serdar. It was very interesting.
It was a pleasure. You all take care. Bye now.
Thank you.
Yeah, bye-bye.